So very good morning to all. So today we have a webinar in the title Opportunities for Engineers in the Field of Plant Design, Construction and Operation, June 7th, 2021. So now I welcome the chief guest of this today function, or today event, Mr. M. Kannan. And I welcome our respected chairman and vice chairman and our beloved principal and all the head of the departments and students and participants from other colleges. I welcome all you people for this today event in the good morning. So this is a great pleasure for all the people of J.N.N. Institute of Engineering. We are in the position of conducting various events in the form of webinars and seminars for the student community to uplift their ideas in engineering. So in this connection today, we have a wonderful guest. His name is Mr. Kannan. Actually, he's a lead consultant engineer in plant design and construction, and he's a founder of EQ Tech Engineering Coimbatore. So now I'm going to say a short synopsis of Mr. M. Kannan. He's a chartered mechanical engineer registered with Institution of Mechanical Engineers UK with 20 plus years of industry experience in design of pipes, pipelines, piping valves, rotating equipments, and everything. And he's a project management lead also. His work experience covers organizations that manufacture equipments like tanks, pressure vessels, heat exchangers, pipeline valves, EPC and PMC, contractors and process plant operators. So especially chemical, refinery, oil and gas. He has handled various positions like design engineer, estimation engineer, project engineer, spanning across various stages of projects, planned life cycle from feasibility study, concept selection, feed, detailed design and engineering, construction, commissioning, and handover to the operations. So currently he is offering consultation with his rich experience and offering training services in the above field expertise through the startup organizations, EQ Tech, students who are interested in shaping their career in the above field and expertise, and those looking for a mentor can contact him and get some useful informations. Now I welcome our chief guest, Mr. M. Kannan, to address the gathering. Please welcome, sir.
Thank you, Mr. Arun. Thank you. And thank you everyone. Good morning, everyone. Ellarkum kaalai vanakkam. So let us start the session today. Initially, before that, I would like to thank the management of J.N.N. College and Professor Arun, Professor Sitharaman, and Professor Shubhashini for giving the opportunity for this session. And today's, I think everybody can see my screen. So today's session is about the job opportunities for engineers and diploma engineers in the field of plant design, construction, operations, and maintenance. So as usual, if any queries is there, please put your queries in the comment box. That will be addressed at the end of the session. This is a small disclaimer. So these whatever information which is shared in this presentation are provided based on my own experience. I does not represent any of the organizations or principal or company's policy. And this presentation will be updated regularly. And if anyone needs this presentation, they can contact me on the mail ID. Okay. So at the end of this session, the participant will understand what are the various components of plant. What does a plant contain? different phases or life cycle of plant from start till operation. And what are the various engineering discipline teams involved in the design, construction, and operation of plant? And what are the projects or type of projects that will be leading to construction of plant? And in these design, construction, and operation, what is the role of engineers? Apart from design, construction, operation, and maintenance, what are the other indirect opportunities that an engineer will have in this field? And at the end, we'll be seeing free membership for students with the Institute of Mechanical Engineers. Let us start the session. What is a plant? A plant is a setup which manufactures or processes a product, be it a refinery or anything, any plant. This is a common definition. And we all know about nuclear plant, the power plant, which we have studied in our engineering curriculum. What we have not studied in the curriculum is oil and gas plants, chemical plants, petrochemical plants, and refinery. So these four plants is what we are going to discuss. Today's discussion will be based on my expertise, my experience in this type of plants. And what you see here is a schematic of a unit in the plant. A plant has different units. This is one of the units. This is a refining section of a refinery. So, what does a plant contain? A plant contains very few items only. When we classify it as in the broad classification, it will contain basically equipments. Equipments, we'll see what are type of equipments. Basically, equipments are classified into rotary equipments, static equipments, or specialized equipments. And when we have different equipments at different position of plant, we need to connect these equipments through piping, where the fluid can be transferred from one equipment to another equipment for processing or storage or whatever it is. Then, instrumentation is there. So, for any fluid, we have to measure the properties of fluid. So, instrumentation is most required part in a plant. Then, civil or structural. A plant will have, for example, for equipments and piping will have foundations, and the equipments or piping will be supported by beams and columns, so that we call it a structural. Then electrical items, like a pump will have electrical motor, and lighting arrangements will be there. So this is where this is what we call as electrical items. These equipments and piping will be handled by mechanical engineers, whereas other part of instrumentation will be handled by instrumentation engineers, and civil and structural by respective civil engineers, and electrical items by electrical engineers. These are examples of few plants and pictures I have. So whatever you see here, big tanks, they are static equipments, and these high-raised towers, we call it columns. These are static equipments, and you can see pipings connecting this one, and these piping supported by the structurals. And what is not seen here in the pictures are the rotary equipments or instrumentation, which will be located in the ground level, and it will be comparatively small to this. It will be comparatively small, so it's not appearing in the pictures. So what does a plant contain? As I said earlier, it contains mainly equipments. What is an equipment? Equipment are classified into rotary, static, and specialty equipments. Under rotary equipments, we will have pumps and compressors and their drivers. Why the name rotary? Because it has rotating component, so it's called rotating equipment. Then static equipments, which are fixed. In some organizations, they call as fixed equipment also. So static or fixed equipments. These are tanks, pressure vessels, heat exchangers, etc. Then specialty equipments are packages. So these specialty equipments are what they call specialty equipments means this will be sometimes a combination of static and rotary. Like some package will have the specialty equipment will have both vessels as well as pumps and piping mounted on the separate skid. We call it skid. It's nothing but a welded frame on which we'll be mounting the equipments and piping and instrumentation. So these are classified as equipments. Piping, as you all know, apart from pipes, there are piping components which are flanges, which connects two pipes, fittings, and their supports. These are commonly called as piping. Of course, valves, pipeline valves are also comes under piping. Instrumentation, as I told, instrumentation has mainly instruments, measuring instruments like pressure gauge, level gauge, temperature gauge, and other specialty gauges. Then control valves. Yes, though control valves is specialized one, so this will be handled by instrumentation, not by piping engineers. And instrumentation cables also will be designed and routed by instrument engineers. And civil structural. These civil structural will have civil foundations and structurals like platform, supports, beams, columns, ladders, platforms, etc. In electrical, we have electrical drivers, then lightings, electrical cablings, which will be running around the entire area of the plant. Now, I would like to show a small video so that you can understand how a plant operates. Actually, I wanted to show this in the operation section, but since this webinar for students, I would like to show it here. So what we are going to see in the video is a unit in which how it is getting operated. So initially from crude storage tank, this is called a schematic diagram. So initially the crude which is stored in the tank is passed on to the crude feed booster pumps. From that pump, it will be transferred to the heat exchanging units. From the heat exchanging units, the piping is transferring the crude oil to a desalter, where it will be desalted, and the desalted crude oil will be coming to a flash drum. It's a static equipment. Then it will be pumped through another secondary heat exchange system, and it will be transferring to the furnace for preheating. Then it is taken to the distillation tower. So this is the setup there. Now let us see the video.
The Chevron Richmond refinery lies approximately 10 miles northeast of San Francisco in California's Contra Costa County. The 2,900-acre facility was initially established in 1902 and primarily makes transportation fuels such as gasoline and diesel, as well as lube oils. The refinery can process up to 250,000 barrels of crude oil per day. The first step of the refining process takes place in the crude unit, where crude oil is cleaned and heated before entering the distillation tower. Inside the tower, the crude oil is boiled. The vapor then condenses into various liquid hydrocarbon fractions, or streams, including jet fuel, diesel, and gas oil. The different streams exit the distillation tower through separate pipes or side cuts that lead to other sections of the refinery. On August 6, 2012, the crude unit was operating normally. Around 3:50 that afternoon, an operator was performing a routine check when he noticed a small puddle on the ground near the distillation tower. The liquid appeared to be dripping from an 8-inch insulated pipe 14 feet overhead. The leaking pipe was a section of the tower's number 4 side cut line, which operated at a temperature of 640 degrees Fahrenheit and contained light gas oil, a combustible liquid similar to diesel fuel. Chevron inspectors knew that over the years, the walls of the number 4 side cut had thinned due to corrosion, but they did not realize how close this particular segment was to failure. There was no shutoff valve between the pipe and the distillation tower, and no way to isolate the leak. The head operator was called to the scene. Although he believed the situation was serious, he did not believe the small leak warranted immediately shutting down the unit and stopping production. Following Chevron's standard practice for responding to hazardous leaks, refinery firefighters were sent to the scene. A number of managers, engineers, and technicians gathered there informally to assess the problem. The group discussed a recommendation from an operator to shut down the unit, but they decided to first try to pinpoint the leak by removing insulation from the pipe while the crude unit was still running. They hoped they could stop the leak with a temporary metal fitting known as a clamp. A Chevron firefighter tried using a pike pole to hook and pull away the insulation, but this poking action was deemed too dangerous because it was moving the pipe. The CSB later found that the tip of the pike likely caused a small puncture in the already thinned pipe. As the unit continued to operate, workers assembled scaffolding directly beneath the leaking pipe. 2 firefighters then used a hook to remove the insulation from the pipe. As they were working, hydrocarbon vapor began to flow out from underneath the insulation. The 2 firefighters backed away from the growing vapor cloud. As the hot vapor mixed with air, it ignited. That fire was quickly put out, and the 2 firefighters immediately climbed down off the scaffolding. But the exact location of the leak was still obscured by the remaining insulation and firefighting water. So the Chevron firefighters attempted to strip the insulation off the pipe with high-pressure water. But the leak suddenly worsened, and hot hydrocarbon liquid started to spray out of the pipe. A decision was finally made to begin an emergency shutdown of the crude unit, but it was too late. Suddenly, the pipe ripped open. A vapor cloud formed and rapidly expanded as the large inventory of hydrocarbons in the distillation tower started to vent through the ruptured pipe. The vapor cloud immediately spread over hundreds of feet, engulfing all 19 people who had gathered nearby. The firefighters and operators struggled to escape through the dense hydrocarbon cloud, unable to see. They had to feel their way out, some on their hands and knees. At approximately 6:30 p.m., 2 minutes after the huge vapor cloud formed, the hydrocarbons ignited. One firefighter was trapped inside a fire engine when it was suddenly engulfed in flames. He radioed for help.
Mayday, mayday, mayday! This is 460!
But when he received no response, he assumed everyone else was dead. To escape the inferno, he fled through what witnesses described as a wall of fire. Fortunately, all the workers would eventually flee to safety, and there were no fatalities. The towering white vapor cloud could be seen as far away as San Francisco on the unusually clear August day. After the ignition, a dense plume of black smoke formed and drifted away from the refinery. The fire continued burning for hours. Over the succeeding days, more than 15,000 people sought medical treatment at nearby hospitals for breathing problems and other symptoms. During its investigation, the CSB determined that the carbon steel pipe installed in 1976 had thinned to the point of failure from an effect known as sulfidation corrosion. Carbon steel piping is particularly susceptible to this type of corrosion, which occurs over time when the steel is exposed to sulfur-containing hydrocarbons at high temperatures. Steel piping that happens to be low in the element silicon corrodes especially quickly. The CSB learned that sulfidation corrosion had caused a major failure at Chevron's refinery in Salt Lake City, Utah in 2002. Chevron then performed an enhanced inspection of the number 4 side-cut pipe at the Richmond refinery. It revealed accelerated thinning in the piping section that would ultimately fail in 2012. Replacement was recommended, but this did not occur, and the section of piping was never inspected again. In 2009, Chevron experts recommended that every segment of high-risk carbon steel piping be inspected for corrosion. However, this was not done. During a maintenance turnaround of the crude unit in 2011, Chevron inspectors examined some, but not all locations along the number 4 side cut and found significant thinning. Some sections were replaced, but managers decided that the line was thick enough to stay in service and that an overall replacement could wait up to 5 more years. According to CSB investigators, a key lesson is that each and every segment of the piping should have been inspected. Most importantly, the pipe should have been replaced much earlier with an inherently safer corrosion-resistant alloy. The CSB also concluded that had the crude unit been shut down when the leak was first noticed, the massive fire likely would not have occurred. The 19 workers would never have been endangered, and the community would have been protected. For more information on the CSB Chevron investigation, please visit csb.gov.
Ground monitor, we're going to supply from this hydrant. We got to supply that ground monitor.
So let us come back to the plant. So in this video, we have seen how the inaction of management, the operation management, has caused a disaster. Luckily, no fatalities has happened. So some things are very important to be implemented as soon as possible, and inspection recommendation is given. So these two are rotary equipments, pumps, the schematic shown. Furnace is special equipment. So let us see what are the stages of this of the plant life cycle. First is design, construction and commissioning. Then finally the operation and maintenance. Actually, all stages has to go hand in hand. Then only there will be proper communication. So normally all stages go hand in hand. And mistakes in design or construction is going to cause a major failure or loss of life during operation and construction. So what we saw in the example, where during the operation, the recommendations of inspection team was not implemented, leading to failure and problems. So this is a design construction operate. What you see here is a 3D model of a facility, and followed by construction of a different facility. And after construction is the operations phase. Okay. So in the plant life cycle, we can classify into design and construction and operation and maintenance. In design and construction phase, normally any project will have a basic design or field, we call it front-end engineering and design, then followed by detailed design, then followed by construction and installation. Then after installation of equipments and piping, we are ready to hand over to the operations for commissioning. And after commissioning, the operations and maintenance will take over the plant and they will start operating the plant. So you can see here in the basic design and field and detailed design, there is overlap. That means sometimes both will go hand in hand. Similarly, detailed design. For example, in detailed design, first they'll be releasing the drawings for civil foundations, so that the construction will first start constructing the foundations for installation of equipments. So everything will go hand in hand for proper project completion. Now let us see the various disciplines involved. The main discipline is chemical engineering or process engineering, mechanical engineering, electrical engineering, instrumentation engineering, civil and structural engineering. Then there is a specialized engineering metallurgy. They'll be responsible for selecting the materials, and they'll be recommending the material selection to the chemical engineers and other engineers. This is project engineering. This is not a special engineering discipline, but any of the engineering disciplines can join the project engineering department. Can be a chemical engineer, can be mechanical engineer, can be electrical, instrumentation, civil, metallurgy. But I'm seeing that mostly either chemical or mechanical engineering are preferred for project engineering. Now let us see what are types of projects. The projects, we have two major classification known as greenfield and brownfield. A greenfield project is one which is built from scratch, right from the beginning. From sometimes it's called a mega project because there will be a lot of cost involved. Right from the land acquisition, then building, then constructing the foundations, then installing equipments, all these things. Whereas if you see the brownfield project is normally conducted, will happen in a already constructed plant, where, for example, they want to change the pipeline or piping, so they will cut the pipe and change the pipe, or they want to install a new equipment, they want to replace equipment or install new equipment. So these projects which is happening in already existing plant is known as brownfield projects. Then there are various models of engineering, procurement, construction, and commissioning. The famous model normally usually preferred is EPC, that is engineering, procurement, construction. There is also another model available which is called EPCC, which is engineering, procurement, construction, as well as commissioning. So we have different contractors, they call EPC contractors in general. So they can provide the services to the plant operators or the end users or the plant owners. There is one more term known as project management consultant. So when a project is started, the operators or the owners, plant owners will appoint a project management consultant to oversee the project. Because a project will have, EPC project will have different units. A plant will have different units of operations. So sometimes if it is a big project, each unit responsibility will be given to a EPC contractor, different EPC contractors. So all these different contractors will be managed by the project management consultant. So now let us see what does a team EPC or PMC will be consisting of. So it's a process department. Normally, chemical engineer will be there in this department. Metallurgy, metallurgical engineer will be there. Rotary, piping and valves, static, and pipelines. These in blue are will be handled by mechanical engineers. Normally, piping and pipeline, there is a small difference. Piping, we call piping. Both the piping and pipelines, they are pipes only, but there the usage differs. Means the piping, we call piping where if the pipes is used within the plant. Outside the plant, suppose if you want to transfer fluid from one plant to another plant, we call it as pipelines. And electrical, civil, structural, instrumentation. There is one more additional department, procurement. Procurement and expediting will go hand in hand. Procurement, basically procurement of all equipments or piping, whatever hardwares. And expediting will be, they'll be expediting the procurement of the items. Sometimes the expeditors will be sitting in the equipment manufacturers set up factory, and they'll be expediting the projects and project control, inspection and welding. Sometimes inspection and welding will be combined with the metallurgical department. So all these departments in blue color, these is where our mechanical engineers can become a part of the organization. This is okay. In EPC itself, there is design and construction. There will be design and construction team. So a graduate mechanical engineer can be anywhere in the rotary department, piping and valves, static, pipelines, procurement, expediting, projects and project control, building inspection. There is one more third-party inspection. It does not come under EPC, but I just mentioned here to tell that there is some more separate entity known as third-party inspection. So they will be providing the inspection services from third-eye point of view, like the operators or the plant owners directly. They will engage with third-party inspectors, and they will report directly to the plant owners regarding how equipment is manufactured. They will go check the quality of the equipments manufactured, quality of materials procured with the manufacturer. And in EPC, PMC construction, we have there will be separate team for construct and installation of rotary equipments. Piping and valves will always be together. And static equipments will be there. Sometimes rotary and static they have same team. Pipeline installation, projects team, building inspection, then the safety. HSE is nothing but health, safety, and environment. This is a general model of organization, organogram, in the EPC organization. This shows the top level, then managed by different disciplines, managed by managers under them. For example, if you go for a mechanical HO will be there. Then under them there will be senior or lead engineers. Then under them there will be junior engineers. Then under them there will be designers. Designers are done by the diploma engineers. This is a common setup in all disciplines. Now let us see what are the qualifications normally expected for the designations in a discipline. A head mechanical, normally the expectation will be around 15 plus experience. Sometimes some organizations require more than 20 or 25 years experience also. Then senior engineers. Senior engineers, anyone greater than 8 years experience, we call as senior engineers. And those engineers who are having more than 15 or 20 years experience, they call lead engineer or principal engineers. So these are different terminologies used across different organizations. Then engineers, there will be anyone less than 8 years experience. Designers are diploma engineers with a good experience. Okay, what do we do in the design phase? Design phase will start with the feasibility study. So the operators or owners will do a feasibility project to check whether this project is feasible in terms of cost, in terms of time, profit, all these things. Then when that is successful, then they go for basis for design or basic design package or basic design engineering package. It will have quite a little bit amount of engineering details. So when they go into feed phase, which is front-end engineering and design, the basic design engineering package will be expanded to bring in more details. So this package will be contributed by all the display engineers, and they'll be developing the package. Then DD, which is nothing but detail engineering project, in which major procurement will happen, and there will be vendors, manufacturers of equipment, or piping will be involved. And What is the output of detailed design stage? The output will be the design documents or deliverables from all disciplines, and these documents will lead to the construction phase. As I said earlier, the first document will be the foundation drawings, where the construction team will be constructing the foundations. And some key deliverables like piping and instrumentation diagram, it requires combined team effort. Like this document will be generated by a process discipline, but the inputs will be coming from all other disciplines. There are many key deliverables. I just said an example. Okay, now let us see what is the opportunities in design for engineers and diploma engineers. So process engineer, what they do, they basically design or size. We call size. Size the equipments or piping and electrical machines. So what should be the size of piping? Whether it's 2-inch, 4-inch, 3-inch. So depending on the total capacity of the plant, they'll be designing the size of the equipments. And there are some other specialized documents like PFD, process flow diagram, and the piping and instrumentation diagram, data sheets they'll be developing, and it will be passed on. These are key deliverables like PFD, PNID, data sheets. It will be passed on to the respective disciplines for their input before releasing for procurement. And whenever there is a interdisciplinary inputs required, there will be reviews, common reviews like design review, in which all teams will be involved. They'll be sitting across the table, and each one will be giving their inputs to finalize the delivery. There are many other reviews, but for time being, I'm just restricting myself to design reviews. So metallurgy, they'll be responsible for selection of materials and corrosion calculations, material selection diagram, developing of special inspection requirements, doing for procurement or construction stage of equipments and piping, and they also will be involved in reviews. So those items which in brown color, so these will be developed by the diploma engineers. The inputs will be given by the engineers. Mechanically. Let us see mechanical piping. So what piping engineers will do? So they develop the piping material specification. Material specification, nothing but a specification to get the material, whether be it piping or valves. We have to have a separate specification, so that based on that we can buy the items. So they will be participating in review. And the important documents of piping discipline is plot plan, piping plan, isometric drawings, material takeoff. Then data sheets and specifications for procurement. 3D modeling. This is one of the main component of design phase. There will be different reviews in 3D modeling itself. There will be 30, 60, 90% modeling reviews. Where again, all disciplines will be sitting together and reviewing the model, 3D model. Then they'll be providing the material request or request for quotation, which is the specification. Then it will be floated to the vendors for their requisition. So they'll be giving the bids, and when we receive the bids, we'll be technically evaluating. We call TBE, and if they require technical queries to be raised to the vendors, that is called TQ. And when we finalize all these things, when we finalize the order, we release the procurement package, which is PR, purchase requisition. Then once we give the order to the vendor, for example, equipment manufacturer or pump manufacturer, they'll be giving the documents for review. For example, drawings and other inspection documents for our review. Normally, EPC company will be doing a review. Sometimes the operators or end users will be also asking for the documents for their review. Then another important thing is pipe stress calculations. In the piping, there are different piping engineers. There are 3 separate sections within piping itself. One is stress engineers. Other one is piping. Layout engineers and material engineers. So 3 sections are there. what layout engineers will be doing is they'll be defining where the equipments will come, how the equipments will be placed, what is the distance between each equipments. This is the duty of layout engineer. Then pipe stress calculation, stress engineers will be there. They'll be deciding how pipe can be supported, and they'll be giving their recommendations for layout engineers to prepare the drawings. Then when our drawings or deliverables goes into construction phase, there'll be some support required from construction end. There could be some errors or they need some changes. So in that case, the piping engineers has to provide support to the construction team. So normally a piping engineer will be deputed to the site to sit there and give some construction support. There are various models. Sometimes if there is no, they'll be sitting in the office itself and giving the support. So it depends. There are, suppose if the students want to know more about the static equipments of piping, please contact us separately. We can schedule a separate session. Okay, let us go to mechanical. Mechanical, we have rotating skip packages as one of the discipline. So as usual, like how piping did, these rotating and skip package engineers will be developing the data sheets of procurement of pumps or equipments or whatever it is. I call hardwares. And similarly, material equation will be there, and TQs, TB, purchase equation will be there, then vendor account review. And as usual, all teams will have to provide construction support. Then static also same like rotary or piping. So they'll be developing data sheets, specifications, then review participating in reviews, vendor document review, construction support. There are separate skills required. If anyone wants to improve their skills, please talk to us for detailed process. And we already discussed this one, pipeline. What is the difference between the pipeline and pipeline? We already discussed. Instrumentation, the same thing, whatever the mechanical engineers do, but from their discipline, with respect to their disciplines, they will be doing, helping in purchase of instrumentation items and preparing drawings for routing the instrument cables, etc. Electrical, instrumentation, and civil all do their respective jobs. Project and planning. The project department is one of the most important department in a setup, EPC setup because they drive the project. So they will be normally interacting with the customers or the end users or the clients or the plant operators, and they'll be delivering they'll be communicating to the discipline engineers. Mainly, they are the drivers of the project. Inspection, welding, and procurement and expediting we already saw. Okay, these are so far we saw the direct opportunities with EPC companies, EPC organizations. Now let us see a few indirect opportunity areas where the students can look to work for. So the vendors or equipment manufacturers like heat exchangers or pressure vessels or valve manufacturers. So each and every manufacturer will have a team like bidding or marketing and estimation, the material procurement, design, manufacturing, building and assembly, inspection, testing, and supply. And we already discussed about third-party inspection services. So how or where our engineers or graduate mechanical engineers can work in the OEM setup or vendor or original equipment manufacturing setup is design, estimation, procurement, manufacturing, inspection, or testing. Some examples of OEM: pipings and pipes. Piping in the sense the piping components like flanges, elbows, tees, gasket, and bolting. So these each component will be manufactured by a different manufacturer. So opportunities available with these manufacturers also in various areas of the production or manufacturing. Prefabricated pipings and piping spools, valves, different type of valves, special valves like pressure safety valves, relief valves, and pumps manufacturers, compressors, pressure vessels, tanks, heat exchangers. Then there are other specialty equipments like skid packages, air compressor kits, separators kits, dehydration kits, electrical drives like motors, control valve manufacturers, measuring instruments for instrumentation engineers, sectionals, prefabricated sectionals. So here structural engineers can work. Okay, now let us move on to the construction area where how engineers can give their support here. The team is almost similar to the EPC model, where the construction team will have chemical and process engineer, mechanical engineer, civil, electrical, instrumentation control, safety, building inspection. It's almost same setup like EPC or the design. Only thing is the work will differ. Let us see a video of a construction phase, how it's happening. This is a greenfield project where the construction starts from the beginning. So after foundation, they are installing the structures for routing the piping. Equipments are installed now. You can also see some piping installed on the pipe rack or the structures.
The Chevron Richmond refinery lies approximately 10 miles northeast of San Francisco in California's Contra.
Okay, now let us go to operation maintenance. So once we construct and hand over to the operations, so what they're going to do, they are just going to run the plant and maintain the output. And normally a plant will be designed for 20 to 25 years of life. I've seen plants going well for more than 40 years. So how they are extending the life of, though the plants are designed for 20 or 25 years, sometimes they extend the life of the plant for more than 40, 50, 60 years. How they maintain the plant. So here also in operations also there are discipline engineers, process, mechanical, electrical, instrumentation. Some civil will be there, but not all will have civil. And importantly, inspection and maintenance teams will be there. So this inspection plays a vital role in the operation of plant because they inspect a piece of equipment for possible corrosion and they recommend for repair or replacement. So inspection team inspects all items of plant. Then in case if there are some changes required, they recommend the maintenance department to either repair, replace, or re-rate or reuse. Repair and replace, students can understand easily. Re-rate means nothing but, for example, if I want to, there is a pressure or there is a piping which is used for particular, which is designed for particular pressure, say 100 bars. and I want to suppose the chemical engineers wanted to use this pipe designed for 100 bar to 120 bar. So whether it can be done or not. So these things are called rerating. Suppose if they are doing it, it's called rerating. So I can rerate a pipe or equipment to a higher pressure, a higher temperature, and you can continue to use it. It depends. Sometimes the rerating may not be possible. And when you do inspection will tell whether the equipment or piping is fit for reuse, or if it is not fit for reuse, you have to replace or repair. So in operation maintenance team, there will be a process engineer, metallurgy and corrosion, mechanical, instrumentation control, electrical. There will be separate technical services, mini EPC, in which very few members will be present, maybe one from each discipline to support the small projects. Pipeline engineers, equipment, projects and control, inspection and testing, safety. And what are the opportunities a graduate and mechanical engineer can look here is can be a part of our tree department, static and pipeline valves. Normally in operations, static and pipeline valves will be looked after by same person only. In some organizations, I have seen both rotary, static, and piping and valves looked after by the same person. So actually, if somebody has experience in, if you go to EPC model, people will be having only static equipment, so piping experience or rotary experience. Whereas in operations, it's totally different. They expect people to have broad expertise. So please, students, please don't restrict yourself to a particular discipline. If opportunity is there, please look into other aspects of mechanical also, so that it will be useful in future. Pipeline, equipment expediting, projects control, projects, inspection and testing, and safety. So these are areas where mechanical engineers can look into to grow their skills so that they can be a part of such teams. Okay, we are going to end, coming to the end of the presentation. So these are technical references I'm providing for your reference. Some journals like International Journal of Pressure Vessel and Piping. ASME has various journals, very good journals, and some magazines where you can see the day-to-day case studies or day-to-day happenings, analysis, and all these things. Hydrocarbon processing, oil and gas journal, offshore magazine. These are only examples. There are many variety of magazines and websites. US Chemical Safety Board. The failure video what we watched in the start of the programs from US Chemical Safety Board. It has very useful videos where they have analyzed the failure and they have found the root causes and provided animation. Please visit US Chemical Safety Board for many useful presentations. Inspectioneering.com, gulfoilandgas.com, lngindustry.com. These are only examples. There are many variety of many websites. So we suggest this career roadmap for students. Early engagement is important for a student for a successful career. We have to identify the field of interest. It can be one field or different fields. Like see, for a plant design and construction is one field. It can be automobile, aerospace, FEM or FEA. It can be another field. So please identify the field of interest. Then the second year or pre-final year, undergo training in the field of interest, and develop your ability, your skills in the same areas by reading magazines and journals, and sustain your knowledge by performing industrial visits or internships, and sustain your skills in the final year by doing a project in the area of interest, and you can present a paper in journals, and keep sustaining your skills, and also continuously update resume in LinkedIn profile, or you can follow professionals in the LinkedIn, and you can ask for a professional when they accept invitation. You can ask for them to be a mentor or can ask to give them a presentation like this, a webinar, 1 hour webinar, half an hour webinar, to know the industry insights. So it will be useful to shape your career in your area of interest, so that you can go into that industry. And final one, I'm a chartered mechanical engineer, and this is provided by institute known as Institute of Mechanical Engineers, UK. They also provide a free membership for students who are studying. They call them as affiliate member. There is no cost. What are the advantages of student member? Affiliate member is, this institute has a lot of professionals from various backgrounds, disciplines. I'm sorry, it's mechanical discipline only, but various backgrounds, various specialization. They are giving webinars in their own area of expertise. At least weekly one they'll provide. So these webinars are nowadays provided free of cost. Of course, there are other specialized trainings provided on cost, but these free webinars are very useful, and I find it very useful, so that I can expand my skills in other areas. So visit imechE.org for starting application process. If you want to be a affiliate member, if you need some help, contact me on my mail ID. Okay, once you become an affiliate member, which is free of cost, the next level will be incorporate engineer, and after that you'll be chartered engineer. So the students can become an affiliate member. Then after gaining 3 years industry experience or academic experience, like professors or lecturers, you can opt for incorporate engineer. Then if you have some 8 years experience, you can go for chartered engineering. Affiliate member is free, whereas chartered engineer and incorporated engineer is on payment, nominal fees, depending on the geographical location, how much you earn. I'd like to give credits to US Chemical Safety Board for using their videos, YouTube for using a construction video, MIMechE, and various internet resources for pictures. Okay, so that's all I have for now. If you have any queries, please. Sir, Mr. Sitaraman or Mr. Arun?
Yes. So students, do you have any queries? Now you can raise them. So sir will assist you. So if you have any doubts, you can. Yes, somebody have some doubt, I think. Okay, any queries from audience?
Okay, just I want to tell something.
Okay, sir, I hope that. Okay.
Sir, 1 minute. I just want to add something. Persons or students who want appreciation for attending this webinar, they can contact me on my mail. I can provide appreciation from my LinkedIn page, so that I can give a recommendation saying that this student has participated in this webinar for 1 hour, so that it will be there in their LinkedIn page. So interested students can contact me on mail. I can give them. Yes, sir. Saru, you can take over.
Yes. So thank you very much, sir. So thank you very much for your valuable speech in the topic about opportunities for engineers in the field of plant design, construction, and operations. So we have got a very good speech and very good ideas about the plant design and construction. So this is somewhat new to us. So we are very glad about. Now I welcome Mr. Venkatesan of third year mechanical engineering to present the vote of thanks.
Good afternoon, sir. Can you hear me, sir? Good afternoon, sir. Myself, Venkatesan, I am hereby representing my vote of thanks to today's event, sir. I am from third year mechanical. I thank the chief guest, Mr. Kannan, for providing an excellent speech about opportunity for the engineers in the field of plant design and construction operation. Then I thank about chairman and vice chairman for providing this opportunity to the students and all. Also, and I thank beloved principal and the head of the department for organizing an amazing event for the students for other colleges. I thank all the participants of J.N.N Institute of Engineering and other colleges and expect the same cooperation in the future also. Once again, I thank all the dignitaries who really helped to make this event successful and request all the participants of the today event to give your continuous support in the future events too. Thank you very much. Thank you all once again.
Thank you.
Thank you very much. Thank you.
Thank you, sir. So let us end the presentation, right?